Earth. To model it is a very complex problem. Earth is a planet with largely water and atmosphere. Let's dive into the physics. Dr. Will Happer is going to describe the nonlinear 5 equations.
Because even the most powerful computers can't solve all the equations needed to accurately describe climate. Some climate scientists replace the highly complex equations that describe the real-world climate with highly simplified ones. They're computer models.
As we turn to the computer climate modeling in more detail, to better understand what Dr. Happer is referring to, we see initially that the computation of the climate occurs at an actual intersection of boxes. And these boxes are piled up to render the atmosphere, the Earth's surface, and the oceans. In this example of global model resolution, you see that the Earth's surface provides a resolution of 150 to 300 kilometers. This amounts to 15 grid boxes across the entire United States, and California rendered in a 2x6 grid. Not very much resolution. So the question then becomes, how does resolution relate to accuracy? In this satellite view of the Earth, you see the complex structure of the clouds and the Earth topology. And in this next picture, you can see that image with the same effective resolution as depicted in the previous section. So this raises questions about how accurate the climate can be determined, since clouds and the topology have a lot to do with how the climate operates. To make up for this lack of resolution and other limitations in how the equations are formulated, there are add-in estimates called parameterizations, and these cover cloud formation, ocean oscillations, and other major natural variables. These parameterizations are actually modified to tune the model output to make it better agree with some selected period of actual measurement. So let's dive into the results of these models and see how they do. In this graph, we see a comparison of climate model runs versus observations. Vertical axis has temperature, anomalous temperature, global, bulk atmospheric temperature, and on the x-axis we have a time period from 1975 to current time. And what we see in this is that the difference between the observation and the average of these climate runs is larger than the actual value of the observations themselves. So this is not boding well for the comparison of model versus observation. To examine the concept of average, which was used in the climate models in the previous graph, what would an average passenger jet look like? So as you can see in this particular depiction, it's a nonsensical image having no meaning. In another example of models versus observed, temperature anomaly for the years 1900 to 2013 for a specific area, the U.S. Corn Belt. And what we see here is that in the blue, or the observations without the urban heating effect, versus the model, or red, we see again a big disparity of models are over-predicting warming. In another diagram comparing model output with observations, we see this model output diagram on the left. The vertical axis is altitude, and the horizontal axis is distance from the equator being at the center. And what we see is that there is a hotspot, as predicted by the models, at about 12 kilometers in altitude, centered at the equator. What we see in the observed diagram on the right, with actual measurements from calibrated balloon temperature sensors, we see no hotspot, and this has been replicated actually several times. In yet another diagram comparing model versus output, we see the results of 24 climate models simulating seasonal and annual cycles on land surfaces. How does this compare with the actual observations? Well, as you can see, the observations are a good deal different than the model parameters. We should turn to the IPCC claims on model versus observations. In this particular graph, we see the IPCC storyline. The models are in red, and the observed data set is in black. And these are 58 simulations averaged from 14 models. So the curves on the right depict the same observations, but compared to the model output without CO2 being input. And so therefore this is a circular argument showing that the emphasis on CO2 is very much a part of these particular computer models. So let's dwell for a moment as to why the circular argument is invalid. What is occurring here is that the model is built based on CO2 dominating the climate, and there's a low sensitivity to other natural contributors. They then remove the CO2 from the next simulation and then compare it to the full simulation. So this is provided as proof positive that CO2 dominates. But no, wait a minute. The circular argument is not proof. We're also left with the question about the other natural causes that are assumed to be insignificant. In this diagram, we can see that the pause of the last 20 years suggests that there's much more at work here than just CO2. So let's have a look at other model concerns. In this list, we have a list of inputs, such as, do we know all the physics? The answer is no. We saw the effects of the low resolution and the lack of complete compute power required for this complex system. The impact of solar variability and biosphere and orbital influences have not been included. As far as the outputs and how they're impacted, cloud formation, and most serious in determining the climate, ocean current and oscillations is also very critical to any sort of determination of final climate. As indicated, the temperature from the tropics to the poles is not computed properly, nor is the rainfall or sea level and ice that occurs around the globe. So what we have is we have a high variability between models and no accuracy estimate either forthcoming.
So we're dealing with a class of problem that's simply too big for any computer and any human mind to attack so far. So it is both. To summarize, it's really related to computing power. Not quite, I would say it's the interacting problem. It's basically the class of the problem is too large for us to tackle.
Compared to water, H2O, carbon dioxide, CO2, is a minor contributor to the warming of the Earth. It's devilishly difficult to predict what a fluid will do. Trying to figure out what two fluids will do in interaction with each other on a planetary scale over long periods of time is close to impossible.
So given all that we've discussed here, how confident are you that the claims of catastrophic future climate are actually real? They are indeed based upon these climate models. Do we know enough to set drastic policies? Should we ignore a good many scientific questions? Is the science settled? Should skeptics be demonized, or should debate be embraced? The question is now to you.